When you do weather forecasting, you're using mathematical models and you have to start your mathematical model from an initial condition to predict forward in time. And so I work on trying to establish those initial conditions, mainly for weather forecasting, but you also use it for climate modelling. In addition, when you want to forecast the uncertainty related to your weather forecast, which is what they do now in operational centres, you need to understand the uncertainty in the initial condition because that propagates forward in time and gives you an understanding of the uncertainty related to the future prediction. This is a snapshot of an example of sea surface temperature from a climate model. It's a climate model developed by the Met Office, and it's one of the models that we're using to do some of the work looking at our data assimilation scheme in terms of climate modelling. Data assimilation is the combination of observations and model fields. This is a snapshot of sea surface temperature at, I think, -5 metres depth. You can imagine that the climate models, this is made up of lots of different points over the whole resolution. The climate models then go right down into the depths of the ocean, and you also have temperature right up into the top of the atmosphere. So you can imagine that's just temperature, and that's over the whole domain for one time shot, and you're getting a lot of information. When you start looking at other variables that you also have in these climate models, you end up with a huge amount of variables that you're trying to establish. So they're very, very large and very complicated systems. So what we have here is a snapshot of this big climate model that we're looking over just one little box that's over the North Atlantic Sea. And what I show here is not sea surface temperature, but sea surface perturbation from a mean height. And this comes from a very simple model that I use to explore the ideas that I research in. And so I'm just looking at a very simple single layer model. In the setup I use, I would be having a wind being blown across the top of this single layer. And then we're replicating the Coriolis force in our big model, which means that as the wind's blown across, the water is pushed across the domain and then it spins down because of the Coriolis force. So you get a period of higher levels of water at the lower end of the model, and at the top you get a deficit in water. So this is a very simple model in terms of the whole climate system, but still quite a complicated model that allows me to test my ideas in data assimilation. I test theoretical ideas using models, so when I do data assimilation, I am looking at a model run that I call the truth, from which I take observations, so I don't work with real observations. When we run these simpler models, we need initial conditions from which we start the simple model, and the same is true of the big climate models that we run. We need to start them from initial conditions, which means that we have to establish what those initial conditions are and also the uncertainty related to those initial conditions. So here you've got the primitive equation model we were looking at before, which is a simple sea surface perturbation model. And what we want to do is we want to run this model forward in time, so we want to start from initial conditions. And what I'm showing here is the track of the satellite, a JSON altimetry satellite going across this domain. So if this was real life and we didn't have our truth, all we'd have is observations going across on the tracks of this domain. And you can see that actually we're not covering the whole of the sea surface perturbation height across the whole of the domain. Now in the big climate models, this won't be the only observations we have. We'd also have observations from other satellites. We'd have temperature observations, and the temperature might relate to the sea surface height. So we'd get a lot more information than just this one altimetry track. There'd also be memory in the system. So we'd have memory from the observations the previous day that would also reflect on our knowledge of the system today. But in order to link up all those different bits of information, what we do is we use a short-term forecast from a previous model. So I would take a model run of, say, a day or 6 days, depending on whether I'm looking at the ocean or the atmosphere, and then I would combine that with the observations I do have. And that gives me an understanding of the initial conditions that I then put into my model to run my model forward in time. And you can do the same sort of thing with climate models. The reason we need to understand these initial conditions is that they can have quite an influence on our future predictions. So another one of the models that we often use in weather forecasting and in data assimilation is the Lorenz 63 model. And so quite a few people might be familiar with Lorenz's butterfly quotation, where he talks about the flapping wings of the butterfly influencing weather in several days' time in different locations. The same person wrote a model that we use to understand a lot of what we do in data assimilation, because it's a simple model that represents some of what we have in the climate, but in a very simplified manner, which means that we can explore our ideas in a much simpler model, but some of what we learn will then be applied for weather forecasting, but also for climate forecasting in terms of the initial conditions. So the Lorenz 63 is a chaotic system, and what it represents is it looks like a butterfly. So when you can see a particle moving, it moves first on one side of the butterfly before switching over onto the other side of the butterfly. And the reason it is so interesting when we do data assimilation is that the initial conditions can have a large influence on the path of a particular model trajectory through this model. This means that if we don't quantify our initial conditions very carefully, we'll end up with a trajectory that moves onto the wrong side of the butterfly and doesn't give us an understanding of what we really see occurring in the weather and in the climate. Now, this is a very simplified model, and it's very easy to see this occurring, but in the much more complicated climate models, you have similar sort of patterns, where if you don't get your initial conditions correct, you can have a different system appearing than the system that actually then occurs in truth.